Good morning, everyone. This is Mr. Keppel. I'm here today with my IBSL physics class, year one. There's no one in the live chat, so I'm just going to be doing this by myself, talking to myself. It's going to be a little weird, but hopefully you guys are able to watch the video and still get something out of this. Today's lesson is about latent heat, or better put, is like the energy of a phase transformation. There's three main ideas that I want to communicate in the lesson today. The first idea is that supplying heat to a body may not necessarily change its temperature. It might change its phase. The second main idea is that there are four changes of phase that we're mainly concerned with, and those are melting, freezing, vaporization, and condensation. So you need to know what those phases are, like what's happening, ascribe those names to a specific transformation that's occurring within the material. And then lastly, specific latent heat is the energy required to change the phase of a unit mass, and that's given that the temperature is constant. So we really want to understand today is like how do you change the phase of a material, and you do that by supplying heat to it, and there's a certain amount of heat that it's going to take to change the phase, and we call that the latent heat. We're going to begin by looking at the same situation we looked at in the previous lesson, which is a sample of water on a hot plate. So we're going to be supplying heat at a steady rate to this sample of water. So I'm going to be supplying heat to a sample of water at a steady rate. And so as time passes, we're going to be adding and supplying heat to this water. And so the temperature is going to change. And so that's what we do is we continuously record the temperature of the water over time. And so when you do that, you get this graph down here. So this is a graph of the temperature against the time. And I'm just making the units arbitrary. Like we're not reading any numbers off here, so I don't need to put any units on this graph. Now, there are several things that happen. So you notice this is what we saw before was the temperature will rise at a steady rate. That's because of the specific heat capacity. So the temperature will rise at a predictable constant rate until it hits point B. What happens at point B is the temperature stops changing. In last class, we said that's because there's a change in phase occurring, that the substance is no longer able, the particles, the water molecules, they're not able to go any faster because they're constrained within their motions. Like they're moving as fast as they can while still being attracted to the nearby water particles. So the temperature stops increasing. But if you keep dumping water or heat into the water, keep dumping in the heat over and over again, eventually you'll reach a point where the temperature is able to rise once again. Man, my voice is like cracking like crazy today. Let me see if I can cough and fix that. All right, hopefully this fixes things up a bit. I haven't really talked much this morning yet. Okay, so what we want to do is basically outline how the heat supplied is going to affect the water molecules during these following time intervals. So we're going to look from A to B, then we're going to look from B to C, and then we're going to look from C to D. And we're going to ask how do the water molecules, how are their motions affected during these time intervals? So we're continually adding the same amount of heat, but the particles aren't going to be affected equally. Let me move this stuff down so it looks nicer. Okay, I just lost my arrow. Okay, so let's talk about that. So from A to B, what we know is happening is that the water is gaining internal energy. So we're adding that heat into the water. And so from A to B, the water is going to gain internal energy. Actually, I mean, that's literally what heat means. It's like you're transferring internal energy to the object. So the object is going to be gaining internal energy. So from A to B, it's going to gain internal energy. So we're just outlining. We don't need to go into too much detail here. All right, so what we know is happening is that two things are happening. Internal energy is two things. If you guys were here, I would ask someone to tell me what it is. So if you don't remember what it is, internal energy is two things. Internal energy is the kinetic energy plus the potential energy. Where we're talking about the kinetic energy of the random motions of the particles, and we're talking about the potential energy and the separation, or like those interparticle forces that are pulling and attracting those particles together. So what's happening is it's gaining internal energy, but it's because of both. You can see that the temperature of this object is rising from A to B. So that means it's gaining kinetic energy, but it's also gaining potential energy. So it's gaining both. So the water molecules are gaining both kinetic and potential. So the molecules gain kinetic energy, and potential energy. And the thing that describes the thing that describes to us the rate at which these particles are gaining kinetic energy, what describes it to us is the specific heat capacity. And so we know that for every, I am running out of space. Let me move this stuff down. What we know is that for every joule of energy, not joule, for every 1 degree increase in temperature, for every 4,200 joules of heat. So every time that we add 4,200 joules of heat to the water, it's going to have gained a degree Celsius. So that's normal heating. Sometimes people will call this, what do they call this? Oh my God, I already forgot what it's called. I got it down below. Let's see if I can find it. Oh, here we go. Sensible heat. So people will call this the sensible heat, or like it makes sense because you're adding heat to this thing and it's getting hotter. That's the sensible heat. The one that we're going to talk about is the latent heat, and that's what's going on in this next region here because you're adding heat to it, but the temperature is not increasing. So this area here is called the sensible heat from A to B, and then B to C is going to be called the latent heat, where it's like hidden. You're adding this heat to the object, but it's not. You're not changing anything. Like you're not noticing any change because the temperature is staying the same. All right, so from B to C, that's exactly what's happening is that we don't have any increase in the temperature. And so why is that? Well, it's still gaining internal energy. Like it's always going to be gaining internal energy. That's what it means when you supply heat to something is you're supplying it the particles in that thing with internal energy. But what happens though is that there's no gain in the kinetic energy. All the energy that we're adding is going into potential energy. And how do we know that there's no gain in kinetic? Because there's no gain in temperature. And kinetic energy is proportional to the temperature. So if the temperature doesn't increase, then the particles aren't gaining any kinetic energy. So what's happening is that the particles are gaining potential energy only. So the molecules gain potential energy only. So what that means is that the particles, the water molecules that are attracted to each other, they are being pulled apart. So there's more potential energy stored in that. So if you were to like cool it off and let it go, they'd come back together again. So what we're saying is that we're pulling the water molecules apart. So the molecules are pulled apart. And what happens is when you pull water molecules apart, they go from being a liquid to being a gas. So what makes the water a liquid is that the water molecules are still attracted to each other and they're moving around. But then when you add energy to pull them apart, now it's a gas and now they're flying all over the place. So what's happening is we say that this energy that we're supplying, it's not going into raising the temperature, but rather it's going into changing the phase. So then once all the water has changed its phase, so once we've gone all the way through here and the last drop of water has been vaporized, now it's all gas, and so now the energy can start to increase again. In fact, what happens when a substance is in its gaseous phase, when a substance is in its gaseous phase, we said that there's no longer any interparticle potential energy. The particles are so spaced out in a gas that they're no longer attracting each other. So there's no potential energy within these. There's no interparticle potential energies anymore. Like we've fully separated the particles from each other. They're no longer interacting. So now when you add energy to this, it can't go into potential energy more because they've been completely separated from each other. They've been freed of their bonds. And so now when you add energy, it can go back into increasing the kinetic energy once again. So molecules are now are so hard to write at this angle. The molecules are now in the gaseous phase, or just say gas phase. So no PE. And so that means that all the heat that we supply goes into the random kinetic energy of the particles. All Q supplied goes to KE. which is going to cause the temperature to go up. So that's the main idea. Like that's pretty much it. I mean, this is it for the lesson today, is just being able to understand this graph and to realize that what's happening is when you're in the sensible heating region, you're gaining kinetic energy. The molecules, that is, are gaining kinetic energy and potential energy. Once you're in the latent heating phase, you're only gaining potential energy. And then once you've boiled all the water off, then you're back to only gaining kinetic energy. So as long as you can understand, that's like literally why we created the concept of internal energy. It's to understand what's going on here and to see that like these particles, that they're changing phase as a result of these energy transformations that are taking place within the molecules. Let's do some calculations with this. That's why I've got the calculator up down there. So let's say that the water has mass of 150 milliliters. So remember what that means. It's 0.15 kilograms. This is water. So we can use the fact that the density of water is 1 kilogram per liter, or 1 milliliter per gram. And then the hot plate is going to be outputting to the water at 100 watts. We'll just keep it simple. We'll choose 100 watts. It's probably a little higher than what you would see in a hot plate, but 100 watts, it's just to make the math easier. All right, what we want to do is we want to figure out the time at B. So we want to figure out how much time it's going to take for the water to reach its boiling point. So we know that I didn't put this down. I didn't say what the starting temperature was. So we're just going to assume it starts at room temperature. So we'll say that the change in temperature is going to be 100 minus 20. So 20 being the starting temperature. So we know that the change in temperature is going to be 80 degrees Celsius. Okay, and so then from there, we want to find the time it's going to take. So how do we do that? Well, we know the wattage, so we know the power, we know how quickly we're adding energy to it. So what we basically need to do is we just need to figure out, well, how much energy did we add to the water? So that's going to be our Q equals MC delta T. So we're just going to take the mass of the water, which is 0.15. I'm not going to put any units here because we know it's going to work out to joules. The specific heat is 4,200. The change in temperature was 80. And so this will tell us how much heat was supplied to the water when it reached point B. Because at point B, it's reached 100 degrees Celsius. It's reached the boiling point of water. And so we're going to calculate how much energy it took during that time. We want to calculate how much energy it took, and then we can, once we have the energy, we can convert that into a power. Okay, so let's start on the calculator. So 0.15 times 4,200 times 80. So that gives us 50,400 joules. Okay, so now what we want to do is we want to turn that into a time. What we know is that Q is equal to power times time. That just comes from the idea that power is energy over time. And so we know that the amount of heat that we get is the power multiplied by the time. Well, we know what the heat is. We know what the power is, so we can find the time. So from this, we can see that the time is just simply the heat divided by the power. So the heat we just calculated is 50,400, and the power was 100. And so this is going to give us, so 50,400, I'm just going to divide that by 100. Do I even need to put that on the calculator? Nope. It's going to be 504 seconds. We can turn it into a time in minutes by dividing by 60. And we get 8.4 minutes. So just put about 8.4 minutes. All right, so we know how long it's going to take the water to reach point B. This point B is at 8.4 minutes. 8.4 minutes. So now our question is, well, how long will it take to reach point C? So point C is the point where all this water, where all the water has boiled away, and we've ripped the water molecules apart, and we've pushed them out into the atmosphere, that they've disappeared. How much time would that take? So it took 8.4 minutes to go from room temperature up to the boiling point. That doesn't seem that long. But how long would it take to fully boil off the water? Like maybe you guys have left a pot of water on the stove, like while it was boiling. Like I know I've done that before. And you forget about it, and then you come back and all the water's gone. And you're like, whoa. So how long does that take? So it turns out it takes 65 minutes. So the time at C is 65 minutes. So here I'm going to put 65 minutes. Come on, get out of there. Oh, geez, I can't even do it. 65 minutes is the time at C. Okay, so how much time did it take then fully from 8.4 to 65, so we're just going to subtract those two. So 65 minus 8.4. So this means it took 56.6 minutes. So the time from here to here is 56.6 minutes. All right, so the question says, calculate the amount of heat supplied to the water from B to C. So that's why I just found out is 56.6 minutes from B to C. So B to C, so the time from B to C was 65 minus 56.6. Nope, I just did the wrong number. 8.4. And so that meant that the time from B to C was 56.6 minutes. And we usually don't like minutes because power watts is in seconds. So we're going to multiply that by 60 to get it back into seconds again. So the time was 3,396 seconds. Okay, now that we know the time, we can find the amount of heat because the amount of heat supplied is just Q equals PT. So we know that the power was 100 watts and the time was 3,396. And so we're just going to multiply that by 100. I don't need to put that in the calculator. 3,396. I did my decimals wrong. Let's say I'm going to add 2 zeros on there. This is going to be 339,600 joules. So 339,600 joules were supplied to the water in that 56.6 minutes. What can we conclude about the amount of energy required to change the phase of water from a liquid to a gas? Well, first of all, it's a lot. So notice that just to bring it to a boil, bringing that water to a boil was only 50,000 joules. But now raising it to actually boil all the water away, same amount of water, right? Not changing its temperature at all, but just literally pulling those water molecules apart from each other. It took 339,000. So it's 340,000 versus 50,000. So it's almost 7 times more energy to vaporize the water than it was just to heat it up. So what can we conclude? Well, let's do a calculation. So if you remember that the mass was 0.15 kilograms, and then the heat was 339,600. So what we'll do is we'll come up with a number that tells us the amount of joules that you need per kilogram to change the phase of water, to boil water. So we can simply just divide those two quantities by each other. So if I take, I'll just show you guys what we define this thing as L. So we say that the latent heat, L, is equal to the Q divided by, I feel like I'm doing this wrong, divided by M, joules per kilogram. Yeah, this is correct. So the latent heat is going to be 339,600 joules divided by 0.15 kilograms. This is supposed to be an L. Let me make it look more like an L. All right, so now I'm going to get what L is. So this is for water. So L is that number. I'm going to remember to multiply by 100. I'm going to divide it by, so now it's 339,600, and I'm going to divide it by 0.15. And so I get 2,264,000. And then the units of this are joules per kilogram. Joules per kilogram. So we call this the latent heat. So this is saying that if you have a kilogram of water, which is a liter, if you have a liter of water, it's going to take 2.3 million joules to boil it, to change the phase of it to from liquid into a gas. All right, I guess I forgot about sig figs up there. So yeah, it is. It's supposed to be 2.3. So I'm going to write that down here. So it's 2.3 times 10 to the 6th is how we should have written that, joules per kilogram. The graph below is typically called a heating curve or maybe a phase change diagram. There's just different names for it, but this is the full one. So like the one we just looked at was only looking at that area there, but realized that really, I guess it wasn't looking at, it was looking at this part up here. But it doesn't have to start as a liquid. It could actually go back and start as a solid, right? You don't have to start as water. You can start as ice. So this is going to actually go back into those other phases down there. All right, so I wanted to identify each of the following phases on the diagram. What the? These are backwards somehow. I don't know how those got backwards. I want to identify the following phases. I want to identify where is it a solid, where is it a liquid, and where is it a gas. And then I want to identify where are the phases changing. All right, so first up, the solid is before A. So over here, this is where it's a solid. Where it's a liquid is B to C. And then where the material is a gas is after D. And the way I know that that's where it's in those phases is because when the temperature goes constant, it's like during these regions where it's constant temperature, that's where the phase is changing. So it could only be in one phase when you have that linear increase in temperature with respect to the heat that you add. That's where you're going to have the sensible heating, which is where you have the specific heat capacity is governing the rate that that temperature increases by. The other regions where it's flat, that's going to be the latent heat. Identify the following phase changes. All right, so melting. So melting is when you take an ice cube and you add energy to it and it turns into water. So where would a ice cube turn into water? Well, that's A to B. So A to B is melting. I don't know if I want to draw this or not. I'll just give it a go. So melting. Whereas freezing, well, freezing is the opposite of melting. So freezing, you just go the other direction. So freezing is B to A. Okay, the next phase change is vaporization or vaporizing, or sometimes we call it boiling. But that's where you're turning a liquid into a vapor. So vaporizing is liquid into gas. So that's C to D. So C to D is vaporization. Now in the British English, they actually use a S for the Z. So don't get confused with that. But since I'm American, I'm not going to do that because it just seems weird to me. And then condensation is the opposite of vaporization. So condensation is where a gas turns into a liquid. And you're all familiar with condensation. If you're drinking a cold beverage, you'll have little water droplets that sort of beat up on the edge of your glass. And those water droplets are actually coming from the gas, the water vapor in the air, where it's exposed to that colder temperature, that the water vapor in the air actually condenses back into a liquid. So the liquid on the side of your cup is not coming from inside the cup, it's actually coming from the atmosphere. It's coming from the water vapor in the air that's condensing onto the edge of your cup due to the exposure of the colder temperature of the glass. So condensation is D to C. All right, so that's a little bit of the terminology. You do need to know all of these words. You need to know this diagram and how everything fits together. It's really important that you know that. Okay, so this brings us to specific latent heat as a concept. Specific latent heat is capital L, and it's defined as the amount of energy required to change the phase of a unit mass, so 1 kilogram or 1 gram. In physics, we always use a kilogram for the unit mass. In chemistry, they use the gram. So the specific latent heat is the amount of energy required to change the phase of a unit mass at constant temperature. So the equation for this is L equals Q over M. You will almost always see this equation written as Q equals ML to go with Q equals MC delta T. So when you have sensible heating, when the temperature is changing, it's Q equals MC delta T. When you have a phase change, it's going to be ML. So here's the thing is that there's actually different latent heats. So you'll notice that for down here, which was the melting and freezing, it's actually you're gonna have a much lower latent heat there than you will for vaporizing. It's gonna be a lot harder to vaporize, or I should say, it's gonna take more energy to vaporize than it is to melt. And so that's why there's actually ends up being two types of specific latent heat. Remember the specific just means it's per kilogram. So the specific in the name is per unit mass. The latent is referring to the fact that the temperature is constant during this process. So it's a latent heat. You're adding heat and nothing's happening, or it seems like nothing's happening. You can't feel the temperature changing. So it's this latent heat. It's like this, it's absorbing the energy without anything really, without the temperature changing. So there's two types of specific latent heat: the heat of evaporation, or you maybe hear that called like heat of vaporization, and then down here the heat of fusion. So we're talking about fusion because it's like you're taking something that's a liquid and you're like fusing it back together again. So there's two. Heat of fusion is when you're melting or freezing, and then vaporization is when you're vaporizing, or Steam is giving me a notification there. So when you're vaporizing or when you're condensing. All right, so the basic way this works is it's just like specific heat capacity. You just get a table and then you look up what the different specific latent heats are. So when you're freezing or melting, you go find the latent heat of fusion. And then when you're boiling, vaporizing, or condensating, you look up that one there. This chart is also giving you the different melting and boiling temperatures for these substances, which is sometimes helpful to know as well, but it has no bearing on the energy. That's just a point where where this is going to occur, and the melting temperature is also based on the melting and boiling temperatures are based on the pressure in the surrounding air, and we're not going to really talk about that at all. So here's the thing: questions about latent heat and specific heat, they can be extremely complicated. So I'm going to walk you guys through an example of a crazy, crazy complicated question. These questions can just get like beastly. All right, so here's the setup. We have an ice cube. The mass is 25 grams. The temperature is 10 degrees Celsius, and it's dropped into a glass of water. The water has mass 300 grams, and the temperature is 20. So the water is at room temperature. So let's just draw a picture of this. So we're going to have a glass, and then we're going to have some water in the glass. And what we're doing is we're dropping an ice cube into the glass. So I'll just draw the ice cube right there. So now this ice cube is dropped into the glass. It's surrounded by all this water. So the water has a higher temperature than the ice cube, so naturally heat will flow from the water into the ice cube. The ice cube is going to melt, it's going to turn into water, but now that water, after it melts, is going to be colder than the surrounding water, and so then that melted water is going to need to raise its temperature up until it reaches an equilibrium temperature with the surrounding water. Yeah, I said it was going to be complicated. It's very complicated. It wants us to calculate the final temperature. So we're going to drop this ice cube in the water and we're going to see, hey, the water's temperature started off at 20 degrees Celsius. What's going to happen to that temperature? Well, we obviously know it's going to lower. And we want to be able to calculate exactly how much it's going to lower if we drop exactly this much ice into it. We're going to be ignoring any heat transfer to the glass. We're going to ignore any heat loss effects at all in this. It's just going to be even more complicated. So we're just going to be ignoring all that and then just calculating an answer. You'll notice that this question gives us the specific heat of ice because it's not the same as water, and this also gives us the specific heat of water. What's important to remember is that the ice doesn't start at the melting point. The ice starts at negative 10 degrees Celsius. So we're going to have three distinct phases that are going to happen for the ice. So it's going to go through raise up the solid, melt the solid, raise up the liquid. So we're going to be going through these three distinct phases. And so I will draw a graph axis. So that's T. And then down here, this is going to be the Q that we add. So as that Q transfers from the water to the ice cube is going to go through these distinct phases. So you can imagine that the water like kind of starts up here at 20 degrees Celsius. I don't mean that to look like a negative sign, so let me just get rid of that. And then the ice is going to start down here at negative 10 degrees Celsius. Meanwhile, the actual phase change is going to be occurring here, which is at 0 degrees Celsius. So what's going to happen is we're going to have to start here with the ice. The ice is going to need to raise its temperature up so that it could start to melt. The ice is going to need to completely melt, and then it's going to raise its temperature up until it ends up reaching some final equilibrium with the ice and the melted ice and the water, and that's the temperature that we're trying to find. So you can see that the water is going to lower its temperature down a little bit to meet in the middle. I don't know if middle is the right word, but just to meet somewhere in the middle, in between. Okay, so we need to calculate this. So you can see that there's three distinct heating phases here. So we have two sensible heating regions and then one latent heat region. So in the sensible heating regions, you're going to have to use MC delta T. In the latent heat, you'll use ML, and then back again to MC delta T. But now realize that down here, this is ice, and up here, this is water. So you're going to have a different specific heat capacity in these two places. So this one's going to need to be for ice, and then this one's going to need to be for water. So that's the plan. So we're going to just start calculating this out. All right, let's do it. Okay, so we know that the total of all of this is going to be equal to Q, which is the energy that the water has given to the ice cube. And then realize that that Q is also going to equal to the negative of what the water is losing. And we're going to have to take all of that into account by the time we're done here. But let's just start with this. I'm totally out of time. I'm just going to keep going. If you guys want to stop the video, you can. You have no obligation to watch more than 30 minutes of this. And this is going to take me a while, but that's because these are really complicated questions. All right, let's do this. So Q, the first thing we notice is that all these masses are the same. So this is the mass of the ice when it was ice. This is the mass of the ice when it was changing its phase. And this is the mass of the ice after it was melted and turned into water. So all of those masses are the same. So I can just factor that out. And then I'm going to have C of ice times a delta T plus L plus C of water times the delta T over there. All right, I'm going to start plugging in now. Okay, here we go. So we're going to get that the heat that the ice gains is the mass of the ice, which we got to look it up. It was 25 grams. So that's 0.025. We're going to multiply by the specific heat of ice, which was also given to us as 2108. We're going to multiply by the change in temperature. So the ice was raised from a starting -10 to a final of 0, which is when it started to melt. So remember that this is just when it's ice, because once it reaches 0, it's no longer ice. It's going to start turning into water. So, but that change in temperature is 10. We're going to add to that the latent heat of ice, which we have to look up here. So for water, which is what we are going through fusion because it's melting. So that's 334. But we have to be careful because that's kilo. So kilo is 10 to the third. So we have to realize that that's 334 times 10 to the third. So I'll write that down here. So that's 334 to the third. So I'll just put 3 zeros on there. Plus, okay, now we're back over to water. The specific heat of water is, come on, move over there, 4186. That's a lot more precision than we are used to. We usually just call it 4200 times. Now this is where we don't know. So we know that it started at 0, but we don't know what it went to. So we're going to do the final temperature minus the initial temperature, which was 0. I'll just put 0. Come on. So minus 0 there. All right, and so that's what we need to solve for. So let's do it. So Q is going to be equal to, we're going to have a whole bunch of like math to do here. It's going to be disgusting. All right, here we go. So Q is going to equal 0.025. You know what I'm going to do is I'm just going to start crunching this stuff on the calculator over here. Okay, here we go. So I'm going to put the 0.025. I'm going to multiply that by this here. So 2108 with an extra 0 on it. 21080. All right, so that's going to give me 527 plus, okay, now I'm going to take the 33000 times 0.025, 8350 plus, and then we're going to have 4186 times 0.025, and it's 104.65 T. Okay, we can simplify this a little bit further by just adding these two together. So 8350 plus 527. So we're going to get that the Q is going to be equal to, that is the most disgusting Q that I've ever written. It's going to be equal to 8877 plus 104.65 T. Okay, so that's our first equation. We're going to need a second equation so that we could solve for T. And the second equation is going to be coming from looking at the water. So this was just looking at the ice. So now we're going to look at the water. Okay, so what did the water do? So the water Q equals, okay, so what happened to the water was we had a mass of water, not ice. This is the water's mass. The mass of the water was 300 grams. So that's going to be MC delta T for the water. So here we go. So we're going to have Q equals 0.3. That's the 300 grams times the specific heat of water, 4186, times the change in temperature of the water. So the temperature of the water, it was a final temperature of T, and it was an initial temperature of 20. Okay, and we also know that the water is going to be losing, so this is going to be a negative. So we just want to get rid of that negative. So I'm going to add a negative out in the front, so that way the negative goes away. Because what we're going to be doing is we're going to be equating these two energies to each other. We're going to be equaling these two equations, and we don't want the negative to mess things up. So we're just going to get rid of the negative. All right, let's do this. So I'm going to do the math. So 0.3 times 4186. So that's our Q. So Q is going to be equal to 1255.8 T. And then we're going to do, that's negative, by the way. Because of this negative, the negative goes through the T. Plus, and we're going to take that same number times 20. So 25116. Okay, so we'll just rewrite this so it looks kind of similar to the one up above. So we're going to have Q equals 25116 minus 1255.8 T. And so now we know that this amount of heat that the water lost is equal to this amount of heat that the ice cube gained. And so now we need to equate these to each other. So just need to make these guys equal to each other. So we'll do that. So 8877 plus 104.65 equals, I forgot my T, equals 25116 minus 1255.8 T. I just had a little glitch with the video there, but it looks like I'm back now. Okay, so I'm just going to solve up the rest of this problem. So we just have to solve for T. That's all we're doing here. We're just going to find what T is, and then we're done. Oh, that's disgusting. Okay, so we're just looking to find what T is. All right, so basically we're going to need to do this term over here is going to need to get added onto that term. And then this term over here, we're going to want to subtract it over to there. Okay, so let's rewrite this. So go ahead. Okay, so we're going to have 12, turn on the calculator, 1255.8 plus 104.65, 104.65. It's going to give us 1360.45 T. It's going to be equal to, so now we're going to take the 25,116, so 25,116, and then we're going to subtract 8877. And that's 16,239. Now we just have to divide both sides by the coefficient in front of the T, so we're going to divide by 1360.45, and we got our answer. So T is equal to 11.9 degrees Celsius. There you go. That's it.